All right, so welcome to class. I hope you all had a wonderful weekend. This is your last day of new notes. Congratulations, you're toward the end of Unit 9 and the end of IEP curriculum. You thought this day would never come, but here it is. So last time I introduced the Nernst equation for non-standard conditions. Okay, not at 1 molarity aqueous solution, not at 25 degrees Celsius. And if of course have a non-metal serving as one of the redox, not at a pressure of 1 atm. Okay, so what you have is this Nernst equation, and we looked at 3 derivations of the Nernst equation. Okay, 3 derivations. The first derivation is the original Nernst equation, which is this. Okay, the electrochemical potential of a non-standard cell is equal to the standard cell potential minus RT moles of electrons, Faraday's constant, ln Q. Q is the equilibrium. Q is the ratio of products to reactants, not at equilibrium. All right. So that's what we looked at last. Good luck at your tennis match. I hope it goes very well. So what we have here is it's basically a plug and chug situation. So you would have wanted to write out the reaction so that you know who's getting oxidized and who's being reduced. And don't forget, when you're looking at this, anytime you see an ion, it's aqueous. That's how you're going to get your Q values. Okay. So what you say here is that you would have looked up on the table the E cell, and you should have gotten the E cell under standard conditions for this is 0.76 plus 0.34. Don't forget you flip the sign for the oxidation, because according to the table, it's always given in terms of reduction potential. But if you're serving as an oxidation, you're going to flip that value. But you never multiply electropotential. You never ever multiply it. Okay. So, and then we say that's equal to 1.10 volts. Now you plug this into your equation, your Nernst equation for non-standard, and you say that E standard cell is equal to, E non-standard is equal to E standard cell minus RT over NF times ln of Q, is it ln or no? ln of Q. Okay. So what you say here then is, okay, you have the following equal, let's see, 1.10 volts minus 8.314 times the temperature. Oh. Because it's under standard conditions, 0.15. Okay, times the 2 moles of electrons being transferred between them, times Faraday's constant 96,500. The AP equation gives you a more specific number. Use whatever the equation sheet gives you for the problems. Okay, and then ln of Q. So what we say here is we have been told that it's 1/10 the Stanishelli whatever cell is assembled to the standard half cell zinc for zinc and 1/10 of that standard concentration for copper. So then that becomes zinc would be on top because it's your product aqueous. So it'd be 1 molar standard all over. This would be on bottom, your reactant species, because we don't ever include solids, and it's 1/10 of it. So 0.1 molar. And you should have gotten a value around positive 1.07 standard. Any aqueous solution that's standard is 1 molar. And it should have been a value around positive 1.07.
What are the sig figs from?
It should be a sig fig. Ooh.
5?
It would be of 3. Because when you add sig figs to the most precise digit place, and your final and then your final value here that you calculated and measured was 3.
We have inside the log one sig fig number.
That's for pH only. It doesn't quite apply here.
No, I think his point is that you have very imprecise numbers inside of the law.
Oh,
I think since they're giving you this assume that they're extra precise.
yeah, they're kind of, I guess you can kind of assume because they're standardized, you can kind of assume they're almost exact. Yeah.
Why does the cell positive? Because on the table, I think it was positive 0.34 negative.
But that 0.76 is the flipping for the oxidation. Because now it's not serving as a reduction, it's serving as an oxidation. Yes.
Is it a coincidence that your E naught cell voltage is really close to your final answer?
It is not a coincidence. It's supposed to be relatively close. Like your cell shouldn't stray like 6 values. Yeah.
In this, is there a reason you didn't use the other version of
The derivation?
Yeah.
No. You could have used the derivation too.
So we've used that on like AP test. They won't get mad that we're not using the right way.
Well, I think they give you both equations.
They don't.
Oh, they don't. So I would then stick with the normal way.
Okay.
Yeah. That's a shortcut that just allows, it just gives you the constant for that,
Yeah.
right? So you could do that. They won't dock you, but I would say they're always looking for super clear, show your work. So I might just, if you do that, that's fine, but maybe write the original equation as variables beforehand. So they know that you know that you're using that Nernst equation.
Okay.
That's all. Okay. So how about this next one? Here we're told we're at equilibrium. So when we're at equilibrium, we can assume a couple things. That the E cell of under non-standard conditions is 0. So that means that what your equation becomes is E naught cell standard conditions is equal to 0.0592, which is the calculation at room temperature, this whole constant right here. That is 0.0592. Okay. All over N, the number of moles, times log of K equilibrium ratio between products and reactants. So what you would find here is that you would find that the E cell, just looking at the table or given values, they always give it to you, is equal to 1.10 volts. Oh, you're in the same equation. So you've already calculated above, and that's going to equal 0.0592 all over the 2 moles times log of K. And what you're trying to solve for is what is the equilibrium constant. So what you're going to do is you're going to simplify this out to get K by itself. And you'll get that K is equal to 10 raised to the power of 37.2. Okay. And then you'll get that K is equal to 1.45 times 10 to the 37, which shows you that at equilibrium, the forward direction, the transfer of electrons to produce zinc 2 plus aqueous and copper salt is highly favorable. Like that's a huge butt number. Okay, so what we would say is the products are in much greater concentration based on that K value. Because remember, K is the ratio between products and reactants. All right, so key ideas for non-standard cells. You should remember the following. One, cell potential, okay, can act as a driving force to equilibrium. Depending on where your cell potential is, okay, it's under non-standard conditions, you want to get to the point where your cell potential is equal to standard condition cell potential, right? So the more your non-standard E is away from your standardized E value, the more transfer you're going to have until you get to that equilibrium point, okay? So cell potential can act as driving force to equilibrium. You want to get to E naught cell, okay? Cells reach a static equilibrium, not dynamic. So this is slightly different than our previous discussion on equilibrium, unit 7. As the cell system approaches equilibrium, the magnitude of non-standard E drops because you get closer and closer to your E naught. Yes.
Because you're getting closer to equilibrium, you're approaching E value of 0, right? Rather than your E naught. E naught is under standard 1 molar condition.
Yeah, is it
Don't you just, if you approach it, be not at zero? Or give zero as you go to equilibrium?
Oh yeah, you're right, you're right. Sorry, I was missing that. Okay, and then as a cell system strays further, wait, could you say that one more time louder? Just because we have a couple people missing, so.
So the cell potential is a driving force to equilibrium, but equilibrium is not the E naught. Equilibrium is an E value of zero when there's no more change, no more cell potential driving the reaction.
There's no more what is the word?
It's a dead battery.
It's no, there's no more gap, but that's not the right word I like to say.
Potential difference, right?
Thank you. Well, what? I don't know.
Physics.
Yeah,
You can connect it to.
we don't have to, but yeah. So anyway, as the cell system strays further away from equilibrium, the magnitude of your E increases. So what we say then is that concentration can determine the direction of spontaneous flow. And that's kind of the end of that. And now all we have to talk about is, okay, what if you don't have a spontaneous redox for your battery? What if you have a redox that's super unfavorable? Your oxidation is higher than your reduction. Okay. So we call that an electrolytic cell. An electrolytic cell is the exact opposite of a spontaneously driven redox reaction. It's an unfavorable redox that you build a battery off of. So electrolysis is, quick reminder, the process of electricity being conducted through an electrolyte. Ooh, that doesn't look like a word. Oh, that still doesn't look like a word. Electricity being, okay, conducted through an electrolyte or an ion producing thing. And I'll just put ion produce. So an electrolytic cell is a device where electrolysis occurs. So it creates a circuit for continuous electron flow that generates an electrical current. Ion produce. An electrolyte is anything that produces an ion that can then carry charge. So like your pool water is an electrolytic solution. Okay, and what it does is it transforms electrical energy into chemical energy. And does anyone know where Hannah is? Anyone? I noticed that she's gone. No? Okay. So here's the main difference that you want to understand between electrolytic cells and electrolysis cells. Sorry, electrolytic and electrochemical cells. Electrochemical / galvanic / voltaic cells, okay, are completely spontaneous redox. So that means you have a negative G value, okay? You have a positive E cell value. It's all good. Electrolytic cells are non-spontaneous redox. You have to force it to happen. So you would have a positive G and you would have a negative E. So electrolytic cells require an outside source of energy. Thus, we often couple it with something else that's more favorable. Okay. But what we say then is that when you're looking at the table, the oxidation is above the reduction. So you can kind of think of it like pushing the electrons down, pushing electrons down to reduction species. Which takes energy if you're pushing it down. So we say that the difference, the value, the magnitude of your negative E cell, your unfavorable voltage, is the amount, the very least, at the minimum amount of electrical outside force. Okay. So then we say that whatever value this is, plus, okay, the extra energy actually required. To drive an unfavorable redox.
The absolute value of the negative E naught cell.
Mm-hmm.
Okay.
Is your over potential, or you could put it as another way, is the difference between what you think it'll take at the bare minimum versus what it actually takes. And it always takes more than you think, because some of that energy gets lost through the circuit. So you're always going to need to provide it with more energy than is necessary in order to drive that reaction. But your magnitude of the negative E naught cell is the bare minimum to even, like, you got to meet that at least.
What is the negative doing?
The negative tells you that that's not favorable redox.
Why do you need it though? Can't you just take it away?
You can. I'm just saying the absolute value of that.
Oh, okay.
Yeah, those are absolute value signs.
Right, but I'm saying like, why, it doesn't make a difference inside of the absolute value.
Well, you would find the value of E naught cell for an electrolytic process is always going to be a negative number to show that it's unfavorable, that your oxidation's above your reduction. And then that becomes the basis for how you calculate how much energy you're going to need to put into the system, because it has to be at least that amount. Yeah. So, for this problem, what you would do then is I'm just gonna, the figure is up here. It's this figure. I'm just gonna give you some of the values just to show you. This is like your dream question, honestly. Redox questions actually tend to be your dream questions because they're super straightforward mathematically. They're just positive, negative. Does that mean I need an extra outside source? No. Yes. Favorable? No. Yes. That's pretty much it. So,
Wait, real quick.
yes.
You said that the E naught cell is the energy required to drive the redox?
No, it gives you an indicator of how much energy you need at the very least to make that happen.
Okay, because I was gonna say, how do you get from there to energy? Because the E naught is in potential,
It's voltage. Yeah.
which isn't energy.
You would have to calculate using Faraday's constant, which we will in a second, to get the charge energy amount. So we calculate and we report it in amps for current. So we're going to do those calculations in a little bit. So what we would say is that predict the voltage required to operate the electrolytic cell in 8.51. What you would find is that this particular example, it's this reaction, 2I minus going to I2 plus 2E minus, and that's the first half reaction. And the second half reaction is nickel 2 plus gaining 2 electrons to nickel solid. And you would find that your E for this oxidation, E naught oxidation, would become negative 0.54, which means, by the way, we're forcing a species that actually is a decent reduction to be undergoing oxidation. And that means we flip the sign, making it a negative. And then the E of reduction for this half reaction for the nickel is negative 0.26. And we would get that our E cell would be negative 0.80 volts, which is very unfavorable. We want a positive E cell. That indicates spontaneous redox, Olivia. So what we would say then is, what would be the required voltage to operate the cell? We would have to input at the very least an electrolytic or electropotential voltage value of greater than or equal to 0.80 volts. That's the very least we'd have to input. We would definitely have to input more because of over potential. Okay, but that's the very least that we would have to input.
So you determine over potential through experimentation. There's no formula for it.
Yeah, there's no formula. Over potential in the end is actually done through experimentation. Like, you just shoot the sucker up with energy, but you start with the baseline that you can calculate. Like, you got to at least fire it up to this much.
Okay.
The reality is it's probably closer to 1 volt that you need more. Yeah. Because oftentimes a lot of this stuff in lab, that these theories that are very good and that are confirmed through lab, there's also times when just lab just completely defies what you would think, or it shows that it doesn't match perfectly, that there's a lot of wiggle room. That just kind of is the nature of chemistry. Like there were days when in lab, I told you guys this, that we make jokes in chem. We were like, we should have just stayed home. We would have been farther along than if we had come in and spent 8 hours just like botching it. And we would do the exact same process over and over again. Like you did nothing different theoretically, and the chemistry just wouldn't work.
You need everything to drive the reaction. Why?
We don't know. I would mix the exact same stuff in the exact same ways, you know, and it just wouldn't work. We'd get nothing. And then the next day we get like 70% yield. I'm like, what? So we don't know. Okay, try the next one on your own. So when you look at the table, you should have gotten for this problem that the E cell is equal to negative 1.60 volts, which means you're going to require, okay, you're going to require at least, if not more, probably more, over potential 1.06 volts to drive this unfavorable redox. Dream question. You will probably get, hey Bryce, what's up? You will probably, not here. You will probably get at least a few MCQ redox and probably one FRQ. It tends to be pretty popular. They really like to also have you study an electrochemical cell. So like they'll give you an electrochemical cell like in this figure, and then that's what they'll provide, and the values of the E naught for in terms of reduction, and then they ask you to do the rest with it. Okay. So here's a summary table of the difference between electrochemical versus electrolytic cells. Electrochemical cells are exothermic and they make electricity. So what they do is they convert chemical energy, spontaneous redox, into electrical energy. But electrolytic cells are endothermic. They transform electricity. They turn electrical energy through your outside source into chemical energy to drive the reaction, the redox. Electrochemical cells are a source of voltage themselves, and electrolytic cells require a source of voltage. Electrochemical cells are 2 half cells, and electrolytic cells are actually 1 cell. They're just in one kind of zone. We've got spontaneous for electrochemical cells, and you've got obviously unfavorable redox for electrolytic. So that means that your E naught is positive for electrochemical and your E naught is negative for electrolytic. Electrochemical, you have the salt bridge constantly supplying the ions necessary to keep the solutions neutral to promote continuous electron movement. There is no salt bridge in electrolytic. And then here we see that the reduction for electrochemical cells is above the oxidation, but obviously for electrolytic cells, reduction is below oxidation, making it less favorable. So you have to push the electrons down, therefore requiring energy. Okay. So, AP examiners, you can study some extra types of electrolytic. It just helps with understanding a prompt. It's not crucial. Like you could figure out the information without having to exactly know what a molten lava is or whatever. But you will see in prompts, they might talk about a molten species. Okay. So this is just terminology. I'm not going to go through this. I even created a hyperlink if you want to watch something more about it. So let's get into now calculating the actual current necessary, what Liam was asking us. Like, how do we actually get from voltage to current? Okay. We're going to use Faraday's law. Okay. Faraday's law, Faraday's constant. So Faraday's law is basically tells us this, that it reveals Faraday's constant, that we need 96,500 coulombs per mole of electrons, okay, to flow through, okay? And then one thing that you should know is another conversion to consider is that 1 amp, which is a current in terms of how we measure currents, is equal to 1 coulomb per 1 second. Okay, Coulomb's law, Coulombic law of attraction. Coulomb is all about charge. Coulombs is a unit that we use to measure charge in. So this is just basically a giant stoichiometry / dimensional analysis problem with redox, okay, and Faraday's constant. So what we have here is, let's say I have a massive solid nickel. Oh, no, I'm trying to figure out what mass solid nickel could be deposited on graphite cathode by passing 15 amps of a current through a solution of NiCl2 for 2.25 hours. So what we would say is this. This is our reaction. We know that we're going to transform nickel 2 plus and we're going to reduce it. 2 electrons. It's going to gain to become nickel solid. Okay. And what we say is, well, I start with the knowledge that I have 2.25 hours. And since right now that's not very helpful, but I know if I get it into seconds, I can relate it to coulombs and amps. And if I get it to coulombs and amps, I can get it to coulombs and moles of electrons, right? And if I get it to moles of electrons, I can get it from moles of electrons to molar ratio of nickel produced. So what I do is 2.25 hours times, okay, 3,600 seconds per hour. And once I get there, I canceled out my hours and now I'm left in seconds. Once I'm in my seconds, I can say, well, for every 15 coulombs, okay, because that's an amp. 15 amps is like saying 15 coulombs per second. Okay, I have 15 amps, which is like saying 15 coulombs per second. I end up canceling out my seconds and I'm left in coulombs. Then I say, okay, once I'm in coulombs, if I can get to coulombs, I can get to moles of electrons being transferred. So I know for every 1 mole of electron transferred, according to Faraday's constant, I have 96,500 coulombs flowing through. So I cancel out my coulombs. And then I say, okay, if I have 1 mole of electrons, well, I know stoichiometrically speaking for this half reaction that I produce 1 mole of nickel solid for every 2 moles of electrons transferred. So I cancel out my moles of electrons. And then if I want to ask myself, what is the mass of nickel? I just say, well, I'm in moles of nickel. Whoa, dear Willikers. I'm in moles of nickel. And I just multiply by the molar mass of nickel. 58.7 grams per mole of nickel. And I get out of moles. And I'm left in grams of nickel, giving me a value of 37 grams of nickel. I can deposit solid nickel if I run 15 amps of current through a solution of nickel chloride for 2.25 hours. Yes.
Sorry, I'm a bit confused on how you went from seconds to coulombs.
Because that's amps. 15 amps is coulombs per second. So whenever you see amps, convert immediately to coulombs per second, and it should be on your equation sheet as well, written somewhere. So go ahead and try the next one on your own. It's just basically taking it all the way back to unit 1 with unit 9 concepts. So what we have here is you should have gotten the following math. You are doing gold and you are reducing it to gold solid. So what you would have gotten was, this is what your conversion should have been. You got 5 grams of gold. From grams, you go to moles of gold. And then from moles of gold, you go to moles of electrons being moved according to your redox reaction. From moles of electrons being moved, you go to coulombs so that eventually you're trying to get to amps, right? So you go to coulombs and you say, well, times Faraday's law, 96,500 coulombs for every mole of electrons. And then you say, well, I need to get to amps current, and amps is coulombs per second. That's my end goal. So I got to get to seconds. Well, I don't have seconds, but I do have 1.5 hours. So I say, well, then I want to get from 1.5 hour to seconds. So I'm going to put hours on bottom initially. And then I'm going to multiply my hours by one for every 1 hour, there's 3,600 seconds. And I will get then that my final answer is I will generate a current of 1.36 amps or 1.36 coulombs per second. Just unit conversion with some of the new concepts. Again, the AP tends to give you a more precise number for coulombs. Please use that number according to the table that they give you. Don't use this one. It's just more precise. This is less sig figs. They give you a higher sig fig. It's like 96,488 or something.
No, it's the higher sig fig one actually more precise?
Oh, shoot. It is, well, sig fig wise it is because those last 2 0 digits, since they don't have a decimal after, it's kind of like, yes.
Will they give us all these, do we have to memorize all these, remember all the tables that we got derived, gold 3 plus 3 minus?
You do not have to memorize the E reduction potentials.
Okay.
Yes, they will always give it to you, or they will ask you to solve for it, given other information. Okay, so connecting Faraday's law with free energy, we now get a fourth equation for calculating Gibbs free energy based off of redox. So what we say here is moving electrons through a wire requires work in joules. So what we say is that volts is equal to work over charge, which is equal to joules per coulomb. Coulomb. Okay, so then what we can get is we get this derivation, blah, 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 and we get that we can calculate the G naught under standard conditions for a process, which is equal to the moles of electrons, negative moles of electrons being transferred times Faraday's constant times the E naught of the cell.
Wait, joules over coulombs?
Joules over coulomb.
So is it just volts?
Volts is joules over coulomb.
Yeah.
Yeah, that's all we're saying. So the spontaneous process will create a negative G, just like what we expect, G naught, and have a positive E naught cell. So all this is offering you is another way to calculate G given different sets of information. Now you're given E cell and moles of electrons, and you don't have anything else. You don't have the Ln. You don't have it's in equilibrium. You don't have the concentration values. You don't have any of that. You just have E naught cell and Faraday's constant and moles of electrons being transferred. That's it. This way you can calculate it now with even less information. It's just another equation. Okay, so this is pretty much plug and chug. What you would find for this sample problem here is when you look at the table, you would find that E naught of the cell under standard conditions is 0.27 volts for their respective redox reaction happening. And the amount of moles being transferred is 2 moles of electrons. Okay, so what you would do is just plug and chug. You would say that this is the Gibbs free energy or thermodynamic favorability is negative 2 moles times 96 500 coulombs per mole, and coulombs is joules per volts if you rearranged above. Okay, because technically Faraday's constant is in coulombs per mole, but we're trying to get the units to cancel. So times mole of electrons, okay, times, since it's in joules, I'm going to convert to kilojoules, okay, just to make life a little bit easier because I think we see that this is a giant butt number. And we can convert to kilojoules at the end. Just kidding. Let's convert to kilojoules at the end. Times E cell, which we calculated to be 0.27 volts. Okay, you would just do that math and you'd find that this is negative 52 kilojoules per mole of reaction. Highly favorable. Okay, and therefore spontaneous. Okay, so it's again another plug and chug. Unit 9 is nice, it's a lot of plug and chug. So try out the next sample problem on your own using this particular G reaction equation. So we decided that next year we're not going to do this because I think I missed information in the textbook on this problem. So whoops. And what you guys want to do is you want to make sure that you have these connections between G, K, and E because they're really helpful and indicative of some of the context that you might need to consider, as well as some shortcuts you could take, right? It was actually a comment from previous AP students that they wish they had studied this relationship more between these three variables. All three of these equations, actually, let me put it this way. These two equations are given on the AP exam equation sheet. This one is a derivation at 25 degrees Celsius, but you're given the original negative RT over NF, okay? So keep that in mind, but you are officially done with unit 9.
That's good, guys.